Hi everyone, welcome to Unit 30 of online course on probability distributions. In the last session, we have considered some numerical problems with respect to geometric distribution. In this session also, we are going to discuss some problems, some numerical examples related with the geometric distribution. Geometric distribution we have defined in two different ways. One, when x is a random variable defined as the number of failures preceding the first success, that is one way of defining geometric random variable, or we can define the random variable x as the number of trials required for getting a success. Earlier, first one, number of failures preceding the first success, and second one, number of trials required for a success. And here some problems related with the second type of random variable, that is, you consider a problem, let x be a random variable having geometric distribution with f of x is equal to q power x minus 1 p, where x is equal to 1, 2, 3, etc. and p plus q is equal to 1. So, if this is the probability mass function, we know x is what? X is the number of trials required for getting a success. So, when we define x as the number of trials required for getting a success, when we are performing Bernoulli trials with a probability of success p, this is the probability mass function. If it is, you have to find probability of x less than or equal to n, or you have to find actually the distribution function, cumulative distribution function, and probability of x greater than n. These are the two matters or two functions we are finding based on the probability geometric distribution random variable. How do you find these two values? So, consider suppose x is a random variable, number of trials required for getting a success, and p be the probability of getting success. So, f of x is equal to q power x minus 1 p, where x is equal to 1, 2, 3, etc. and p plus q is equal to 1. So, you are given that x is the number of trials required for getting a success, and f of x is equal to q power x minus 1 into p, where x is equal to 1, 2, 3, etc. and p plus q is equal to 1. And our problem is, you have to find what is our probability of x less than or equal to n. So, actually this is the cumulative distribution function. So, what is the probability of x less than or equal to n? By our definition, this is x is equal to 1 to n q power x minus 1 into p. See, this is our definition of probability of x less than or equal to n, that is starting from x is equal to 1 to n, q power x minus 1 into p is added. Simplifying, so this is actually sigma n is equal to 1 to x is equal to 1 to n q power x minus 1 into p, and that is p into, this is 1 plus q square plus etc. up to q power n minus 1. So, when we are substituting the different values for x, we have p into 1 plus q square plus etc. up to q power n minus 1, and that is equal to p into 1 minus q power n divided by 1 minus q, because it is a geometric series, finite geometric series, and that is equal to 1 minus q power n. Why? Because 1 minus q is equal to p, that is actually p into 1 minus q power n divided by p. So, 1 minus q power n is our probability of x less than or equal to n. So, we have established that probability of x less than or equal to n is equal to, the value is equal to 1 minus q power. See earlier, 1 minus q power n, or we can write this is 1 minus, this way also we can write. And if it is, what is our probability of x greater than n? That is 1 minus probability of x less than or equal to n, that is 1 minus p all power n. So, we have obtained cumulative distribution function and the complement of that, probability of x greater than n. So, these are the values related with the random variable x. You consider next problem, that is an example how to identify the parameters of the, here the parameter for a geometric distribution we know only one parameter p, and to find the parameter we have to, we are given that the mean and variance value. Suppose we have the geometric random variable, both ways it is not given which distribution, which form of the random variable is not given to you. So, let us assume that x is a geometric random variable with the usual f of x, that is q power x into p. If we are using that form, and mean is equal to what? Mean is equal to q divided by p, and variance is equal to q divided by p square. So, suppose you are given that geometric distribution for a random variable x, where x is the number of failures preceding the first success is given to you, that is f of x is equal to q power x into p, where x is equal to 0, 1, 2, 3 etc. And mean is equal to the general expression for mean and variance are q divided by p and q divided by p square respectively. And so, you are given that q divided by p is equal to, mean is equal to 3 and q divided by p square is equal to 4. So, that means it is 3 by p is equal to 4. So, substituting q divided by p here, it is q divided by p into 1 by p, that is p is equal to 3 by 4. So, that is the way of finding the parameter of the distribution. If we are assuming x is a geometric distribution with this type of probability mass function. And another problem, suppose you are given moment generative function, identify the distribution with the moment generative function mxt, that is mxt is given as 5 minus 4 e power t or power minus 1, hence obtain mean and variance of the distribution. Here it is, suppose we have the problem here is the moment generative function mxt is equal to 5 minus 4 e power t or power minus 1 is given. And if it is, how to find the mean and variance of the distribution. And we can find the mean and variance of the distribution using this moment generative function by the usual technique, that is either differentiating the moment generative function and put t is equal to 0, you will get arbitrary moments. First derivative give us the first arbitrary moment, second derivative give us the second arbitrary moment, and hence you can find the mean and variance. That is one method. Or you expand the moment generative function if it is possible to expand, and find the coefficient of t power r divided by r factorial, and that coefficients give us the arbitrary moments. That way also we can find. But here the problem is something related with identifying the distribution. So, the identifying the distribution means it is actually, suppose for a geometric distribution x follows geometric, suppose you are given that mx, the x is a geometric random variable with a parameter p, and f of x is equal to q power x into p, this form, suppose, and we establish that moment generative function is equal to mx t is equal to p divided by 1 minus q e power t is the moment generative function we have already established. Here the moment generative function is given as 5 minus 4 e power t or power minus 1, or that can be written as 1 divided by 5 minus 4 e power t, or that can be written as 1 by 5 divided by 1 minus 4 by 5 e power t form. So, divided numerator and denominator by 5, you will get this. So, this is the moment generative function given to you, and that is similar to this form. Okay. We have the result that x is a geometric random variable with the parameter p, where p is equal to 1 divided by 5, and hence if p is equal to 1 by 5, p is equal to 1 by 5, suppose we are finding mean is equal to q divided by p, and this is q is equal to 4 by 5. So, this is 4 by 5 divided by 1 by 5, that is 4, and variance is equal to q divided by p square, and that is equal to q divided by p, q is 4 by 5 divided by 1 by 5 the whole square, or that is 20. 4 by 5, yes, yeah, 20. So, that is the variance of the distribution. So, that is the problem in which you are given the moment generative function that is similar to the moment generative function of a geometric random variable. So, equate the given moment generative function to the function form of the moment generative function of the geometric random variable, and by which you can identify the parameter value p, and if we obtain the value p, then you can find the any quantities related with that distribution. That is, if mean is the question is about mean, you can find the mean. Question is about variance, you can find the variance and other probability values. And this is another problem. This is a problem associated with the geometric random variable and very interesting also. If x and y are two random variables, each representing number of failures preceding the first success. So, that is a first form of the geometric random variable in a sequence of Bernoulli tiles with the probability of success p. Find the probability of x is equal to y. Okay, you add this. If x and y are two independent random variables, then only we can find this. Suppose you are given that x and y are two independent random variables, each representing number of failures preceding the first success in a sequence of Bernoulli tiles with the probability of success p. Find probability of x is equal to y. How do you find this probability? So, you are given x and y are independent geometric random variables. So, probability of x is equal to some k, it is q power k into p, and probability of y is equal to some r, it is q power r into p, where k is equal to 0, 1, 2, etc. And here also R is equal to 0, 1, 2, etc. And P plus Q is equal to 1. So, this is given to you. If x and y are two independent geometric random variables having the probability mass function like this. And the question is, find probability of x is equal to y. Probability of x is equal to y. That is, you are asked to find probability of equality of two random variables. How it is possible? That is, this is equal to, if x is a random variable having the value k, then y should be also equal to k, then only x is equal to y. And what are the possible k values? All possible values of the geometric random variable, that is k is equal to 0 to infinity. So, this is the way we are finding probability of x is equal to y. So, probability of x is equal to y sigma k is equal to 0 to infinity, probability of x is equal to k, x is equal to k, y is equal to k. And since the random variables are independent, you can write this expression as sigma x is k is equal to 0 to infinity, probability of x is equal to k into probability of y is equal to k. This is possible only for independent random variables. And now substitute the values. Sigma k is equal to 0 to infinity, probability of x is equal to k, that is q power k into p. And probability of y is equal to k, that also q power k into p. And that is p square sigma k is equal to 0 to infinity q power 2k. So, that is our probability of x is equal to y, p square into sigma k is equal to 0 to infinity q power 2k, and that is equal to, so that is p square into sigma k is equal to 0 to infinity q power 2k. And expanding this equal to p square into 1 plus q square plus q power 4 plus q power 9 plus etc. Sorry, q power 6 plus etc. And that is equal to p square into, and this is a non-series, this is 1 minus q square. See this is actually p square into 1 plus q square plus q square the odd square plus etc. So, this is equal to 1 minus q square power minus 1, or that is p square divided by 1 minus q square, or p square divided by 1 minus q into 1 plus q, that form you can write. And that is 1 minus q is p, so 1 p is cancelled, so p divided by 1 plus q. So, we have the value probability of x is equal to y is equal to p divided by 1 plus q. An interesting property of the geometric random variables, if x and y are independent geometric random variables having the same parameter p, then probability of x is equal to y is obtained by, probability of x is equal to y is obtained by p divided by 1 plus q. Okay. And next question, that is also a very interesting question, that is, you are given that x and y are two independent geometric random variables that with the same parameter, and given that probability of x is equal to k is, instead of the general value q and p, general values of p, that is probability of getting success, you are given that it is 0.25 is our Q and 0.75 is our P. So, Q power K into P is given as 0.25 power K into 0.75, where K is equal to 0, 1, 2, etc. Find the probability of X is equal to, X greater than Y. And this is probability of X is equal to K is equal to 0.25 power K into 0.75, where K is equal to 0, 1, 2, 3, etc. This is given. This is actually, it is a geometric, this is a geometric random variable with the parameter P is equal to 0.75. And our problem is to find probability of X greater than Y, where X and Y are having the same probability mass function and they are independent also. So, X have the probability mass function like this, Y also have the same probability mass function, and given that X and Y are independent. And if it is, as in the previous case, here also you consider the concept behind probability of X greater than Y. What is the meaning of probability of X greater than Y? Probability of X greater than Y means if we have, suppose you consider the probability of Y is equal to some value, say R, suppose Y is equal to R, what are the possible values for X? X should be larger than Y. X should be larger than Y means it is integral values, so maybe R plus 1, R plus 2, etc. And what are the possible values of R? So, R is any value, it is R is a geometric random variable, so R is a value from 0 to infinity. So, probability of X greater than Y for a geometric random variable is obtained on the basis of finding the sum of this probability over different R values. So, probability of Y is equal to R, intersection X is equal to R plus 1, R plus 2, R plus 3, etc. And that is equal to, you can write probability of Y is equal to R, and see you are given that X and Y are independent. So, this is probability of Y is equal to R into probability of X is equal to R plus 1 or R plus 2 or R plus 3, etc. Okay. So, that is equal to sigma R is equal to 0 to infinity, probability of Y is equal to R into the probability of X is equal to R plus 1 plus probability of X is equal to R plus 2 plus etc. So, from the previous step we have this expression, and now substitute the expressions we have. So, sigma R is equal to 0 to infinity, probability of Y is equal to R means 0.25 power R into 0.75, this is given to you, the given value, into, and this is actually, this value is sigma X is equal to R plus 1 to infinity 0.25 power X into 0.75, that way. Okay. Or sigma R is equal to 0 to infinity 0.25 power R 0.75. Just think of this expression. When x is equal to r plus 1, this is 0.25 power r plus 1, 0.75. When x is equal to r plus 2, this is 0.25 r plus 2, 0.75. So, that means 0.75 is common and 0.25 power r plus 1 is also common. So, remaining this is actually 1 plus 0.25 plus 0.25 the whole square plus etc. So, this is summation of this expression, and this bracket quantity, that is 1 plus 0.25 plus 0.25 the whole square plus etc. is actually, this is 1 minus 0.25 or power minus 1, this expression, and that is 0.75 power minus 1 or 1 divided by 0.75. So, this is actually 1 divided by 0.75, and so this 0.75 is cancelled, and so remaining it is sigma r is equal to 0 to infinity 0.25 power r 0.75. This 0.75 is cancelled with this one. So, 0.25 power r plus 1. So, that is the final value we have. Sigma r is equal to 0 to infinity 0.25 power r, 0.75 and 0.25 power r plus 1. So, that is equal to sigma r is equal to 0 to infinity 0.75 is common, 0.25 power 2 r plus 1. So, that is the final value we have. Let me see, 0.75 is taken outside and this 0.25 and 0.25 power r plus 1 and this power r are combining, you will get 0.25 power r plus 1. So, that is 0.25 power 2 r plus 1 is expanded, you will get 0.75 into 0 r is equal to 0 means this is 0.25, r is equal to 1 means 0.25 power 3, 0.25 power 5 plus etc. or 0.75 into 0.25 1 plus 0.25 the whole square plus 0.25 the whole square the power 2 plus etc. or that is 0.75, 0.25, 1 minus 0.25 the whole square power minus 1, and that is 0.75, 0.25 whole divided by 1 plus 0.25 and 1 minus 0.25, and that is equal to, this will be cancelled with this one. So, 0.25 divided by 1.25. So, ultimately we have the value, this value is equal to 0.25 divided by 1.25, that is equal to some simplifying 0.20. So, this is a very interesting numerical example of a geometric distribution. If you are given x and y are two geometric random variables, independent geometric random variables having the same parameter, generally we can have the parameter p, instead of that one we have the value p is equal to 0.75 is given, and so the probability of x greater than y is 0.25. Now, consider another example that is also associated with the geometric distribution. If y represents the number of failures preceding the first success in a Bernoulli sequence of trials with the probability of success p as given as 1 divided by 3, find probability that y is an odd integer. So, this is a problem where y represents what? Number of failures preceding the first success. So, number of failures preceding the first success here y, our one number of failures preceding the first success. Okay. So, that means probability of y is equal to k is equal to q power k into p, where k is equal to 0, 1, 2, 3, etc. This is given, where p is the probability of getting success, p q plus p is equal to 1. And the problem here is, what is the probability of y is an odd integer? Y is an odd integer. Y is number of failures preceding the first success. So, what is y is equal to? Y is equal to 1, 3, 5, etc. What is the probability that y is equal to 1 or y is equal to 3 or y is equal to 5, etc. So, to find this, you consider this is equal to, we know probability of y is equal to 1, 3, 5, etc. means probability of y is equal to 1 plus probability of y is equal to 3 plus probability of y is equal to 5, etc. Okay. And substitute the probability values. What is probability of y is equal to 1? Q power 1 into p. And this is q power 3 into p. It is q power 5 into p plus etc. And that is p into or qp is taken outside 1 plus q square plus q power 4 plus etc. Or that is qp into 1 minus q square all power minus 1. By this is 1 plus q square power 2 plus etc. So, this is a non-infinite series and the value is equal to 1 minus q square power minus 1. So, that is equal to qp divided by 1 minus q square, and that is qp divided by 1 minus q into 1 plus q, or that is q divided by 1 plus q, because 1 minus q is p and that p is cancelled. And given p is equal to, you are given the problem p is equal to 1 divided by 3. So, q is equal to 2 divided by 3. So, this is given in the problem, that is probability of getting success is 1 divided by 3, and so q is equal to 2 divided by 3, and that is equal to, you just substitute 2 divided by 3 divided by 1 plus 2 divided by 3, or that is 2 divided by 5, 3 win. So, 2 divided by 5 is the probability of getting y as an odd integer. So, when we are performing a random experiment until a success is obtained, and suppose x is the or y, here the variable is y, is the number of failures preceding the first success, then you can calculate probability of y is an odd integer, or y is an even integer also similarly we can calculate. So, probability of y is an odd integer is obtained as q divided by 1 plus q, and that is a general expression, and for the given problem you are having the value p is equal to 1 by 3. So, q is equal to 2 by 3. Substituting, you will have 2 divided by 3, 1 plus 2 divided by 3. So, that means 2 divided by 5 is the answer. So, these are the numerical examples related with the geometric distribution. So, with this, let me wind up this session here, and we will discuss more numerical problems related with the other distributions, negative binomial distribution and hypergeometric distribution in the succeeding sessions. So, thank you for listening. Thank you once again.